Hello everyone. I welcome you all to this new video where I will be talking about linear regression. In this video, I will focus not just on the theory aspect of it, but I will also show you how you can practically build linear regression models. A linear regression is a statistical method for modeling the causal connection between two or more variables by fitting a linear equation to observed data. Regression models are highly important and most commonly use statistical methods for making inferences and predictions. Now let's just see how it works. The first step involves the collection of sample data. In sciences, we can call this as experimental data or observations. In the next step, we make a statistically robust model that works for our sample data. And in the end, we make predictions for large population based on this model. This is generally how our dataset looks like in the form of rows and columns. Each row generally represents a data point or a sample, and each column represents independent variable. There are other names for them as well, such as feature, descriptor, or predictor. Finally, we have a dependent variable or target. In here, y is a function of the independent variables x1, x2, x3, and so on. And regression model is a linear approximation of this function. The simplest linear regression model is the one with the single independent variable. And the corresponding equation would look something like this, where y is equal to beta 0 plus beta 1 times x1 plus epsilon. Now let's go deep into the meaning of these values. Y is our dependent variable or target that we wanna predict based on the value of x1, which is our independent variable. In fact, the prerequisite for regression is that y must depend upon x in some causal way. Whenever there is a change in x, such change must be reflected in y. Beta 1 represents change in y for a single unit change in x1. As an example, if the value of beta 1 is 10, that means for a single unit change in x1, y becomes 10 times. The other component is beta 0 or constant. You can think of beta 0 as the minimum value that y must possess no matter what the value of x1 is. So if the value of x1 is 0, the value of y would be equal to beta 0. Epsilon represents the error of estimation. It is the difference between the actual value of y and the one predicted by the model. It represents the unobserved factors that affect y but are not captured by the model. On an average across all samples, the error is 0. This is the original formula which was written in Greek letters for regression. In practice, we use this linear regression equation where y hat is equal to b0 plus b1 times x1 plus e hat. Now, the big question is, how do we get this equation? The first step is to draw a scatter plot between independent variable and dependent variable for various data points. In this example here, I have 6 data points. This plot might reflect the trend in the data. For example, here we can see increase in the value of y with increase in the value of x, but this does not has any predictive power. In order for this to be predictive, we need to have a best fit line or regression line. And in order to get this regression line, we can use ordinary least squares method. The goal of ordinary least squares regression is to find the coefficients of a linear equation, the slope and the intercept, that minimize the sum of the square differences between the observed values and the values predicted by the regression line. The coefficients b0 and b1 are estimated by minimizing the sum of the square differences between the observed values of the dependent variable and the values predicted by the linear equation. Now, if you remember, we had this scatter plot. In order to draw a best fit line using least squares method, just we need to draw a horizontal line parallel to the x-axis. Then we need to determine the residues. Here d1, d2, d3 and so on represent the residues or difference between the observed value and the horizontal line. Next we need to square them up and add them together. Just like that. And we are gonna be calling this as SSR, or sum of squared residues. Next we are gonna be rotating this line a bit, followed by determining SSR for this plot. Similarly, we are again gonna be rotating this line a bit more, and once again we are gonna be calculating the sum of squared residues. In this manner, after a couple of iterations, we will have a plot between sum of squared residues and different rotations. The rotation with the minimum sum of squared residues value would be our best fit line. So this is how we are gonna be determining our regression line. Once we have the regression line, this would aid us in determining the linear regression equation. The scattered points are the observed values. The distance between the observed value and regression line is the estimator of the error term called epsilon or E. B0, which is the constant, is the intercept on the y-axis. And B1 is the slope of the regression line. Now if you draw a perpendicular from an observed point to the regression line, the intercept between the perpendicular and the regression line is a point with the y value equal to y hat. So given an x, y hat is the value predicted by the regression line. In this manner, we can have a predictive linear regression model. Now the next big question is how good the fit is. We can get the answer in quantitative terms by calculating R square. Now in order to quantize the goodness of fit, we need to compare our best fit line with the horizontal or mean line. For that, we again need to calculate the sum of squared residues for both these plots. And then calculate R square based on this formula, which is the difference between the sum of squared residues between the mean and best fit line divided by the sum of squared residues of the mean line. Now let us suppose SSR for the mean line is 32 and for the best fit line is 6. Now let's just plug these numbers into the equation above. And the number that we have got is 0.81. That basically means that there is 81% less variation around the best fit line than the main line. So R square is generally a number between 0 and 1. The value of 0 indicates that the model does not explain any of the variability in the dependent variable, while a value of 1 indicates that the model explains all of the variability. Generally, a higher R-square value suggests a better fit of the model to the data. There is another metric that we need to consider while analyzing our model, and that is p-values. P-values are numbers between 0 and 1 that quantify how confident we are in the model. Smaller the number for a particular feature or descriptor, more relevant that feature is. Normally, the threshold is 0.05. Now, I'm gonna practically show you how you can build these linear regression models in Excel. Before that, let's just have a look at our problem. Here I have a data set containing data points for 20 organic compounds, where molecular weight is our independent variable and solubility is our dependent variable or target that we want to predict based on the values of molecular weight. In other words, we want to build a regression model where solubility of organic compounds is a function of their molecular weight. We are also gonna see how good the fit is with the help of R-square. P-value will tell us whether the molecular weight is a relevant descriptor or not for the solubility model. So let's just jump onto the Excel notebook. Here is an Excel sheet containing name, molecular weight and log solubility values of 20 organic molecules. Now in order to make a regression model, first what we have to do is select both of these columns. Now go to Insert. Here you can see this scatter plot symbol. Just click on this. In the scatter section you will have many options. We are gonna be going with the first one. Just click on this. Here you have the scatter plot between molecular weight and solubility. Now if you want, you can change the background as well. I'm gonna go ahead with this one. Now once you have the scatter plot ready, all you have to do is go to this quick layout tab and select on this layout number 9 which has FX in it. So let's just click this one. So here you can see we have built our linear regression model. This is the best fit line and this is the linear regression equation where y is equal to minus 0.0183x plus 0.0252. The value of R square is 0.5373. That basically means that we have an average fit here and the model explains any of the variability in the solubility in a moderate manner. Now there is another way you can do it which will give you more information about this linear regression model. So for that what we have to do is go to this data tab. Here you will see this data analysis button. In case you don't see this, go to tool section and go to Excel add-ins. Here make sure you have analysis toolpack add-in turned on. Click OK and you will be good to go. Now let's just click on this button. In here you have many options for data analysis. I'm gonna go with regression one. Press OK. Now in input Y range we have to put the values of our dependent variable which is solubility here. All you need to do is select this column over here. In the input X range we have to input our independent variable which is molecular weight. So just click here and select this column. Turn the labels on, and in the output range you just want to mention where you want to print the summary of this regression model. So I am just clicking here. It has automatically taken the value of index position 24. So let's just click OK, and here you can see we have the summary of our regression model. Now let us just compare this to what we did before. Here you can see the R-square value is 0.5373, and this has given us the same value. Now the value of slope is minus 0.0183, and you can find the value of slope or beta 1 here. The value of intercept or B0 or beta 0 is 0.0252, and that's over here. Now regarding p-values, you have to look at the p-values of the descriptor here. Now here the descriptor is molecular weight, so we have to look at this value, and I told you generally it should be less than 0.05, and we have a value of 0.0002. That means molecular weight is a very relevant feature. So in this manner you can build a linear regression model in just a couple of minutes. Please let me know in the comment section if you have any questions, and if you are interested in these kind of videos, you can consider subscribing this channel. Thank you for watching.